Hi guys, it's Mr. Krieger. This lesson is Inference without the calculator. You should receive this review, reference sheet. I sent it to you, I emailed it to you. Okay, we're going to use this. The reason why I wanted to do this now is based on the fact that we're doing this online testing and that they're not expecting that everybody has a graphing calculator. They might be designing it so that you would need to do some of the formulas. So I wanted to show you how to do inference without the calculator. You'll be able to use a calculator a little bit, but without using the test button, the stat tests. So I wanted to go through with you how you would do that, okay? So this is going to be in two parts. I'm going to do the first two questions from the lesson that I sent you. The one that says how to perform hypothesis tests and confidence intervals using the formulas. We're going to do the first two questions now, and then on the second video we'll do the next two questions. Okay, so let's take a look what we have here. In the past, the mean score of the seniors at South High on the American College on the ACT tests has been 20. This year, a special prep course is offered, and all 53 seniors planning to take the ACT enrolled in the course. The mean of the 53 ACT scores is 22.1. The principal believes that the new course has improved the students' ACT scores. Assume that the ACT scores for seniors are very normally. Okay, so you got that one of the conditions is met here with a standard deviation of 6. This will be the population standard deviation, so we're going to use a z-test and not a t-test. And again, you're not using the calculator for this. I'll show you what you're going to do. And we're going to use an alpha value of 5%. All right, so in terms of all the conditions being met, we know it's normal because they said it in the problem, but you're going to still write that down when you check your conditions. You want to make sure it's a random sample, make sure that it says that random sample, and make sure you mark that down, write that down. And then independence. There has to be at least 530 seniors at the school in order to meet the independence condition. So you're going to have to say there need to be 530 seniors. Now, in terms of doing the test, first thing you normally do, you're going to write down your null and alternative hypothesis. Your null hypothesis is that mu is 20. The score on the ACT tests we expect them to be 20. The alternative is that this new preparation is going to cause the scores to increase so that mu is greater than 20, right? So now, how do we actually do this? If we're not letting the calculator do the test for us, how are we going to do the test? Well, we're going to go to our reference sheet, and we're going to look at this. See, it's a standardized test statistic minus parameter over the standard error of the statistics. That means statistic, so here's going to be, z is what we're computing. It's going to be the statistic, which is x bar, minus the parameter, which is mu, over the standard error, which in this case is going to be sigma over the square root of n. Okay? Now you might say, how am I supposed to know this stuff? Well, on your reference sheet, let's see if they give you anything addition. Yeah, for example, parameters for sampling distributions. Random variable is x bar. The parameter is mu. The standard deviation is sigma over the square root of n. And if you're going to be using a t-distribution, in other words, if you know that you don't have the population standard deviation, you're going to use this one. So those are going to go here for you. The sample mean, the population mean from here, and your standard error. All right, so let's plug this stuff in. So z is going to be equal to 22.1, that's the x bar, that's what the students got on the exam after they took this prep course, minus 20, that was the population standard deviation, population mean, mu, and then we're going to put, for the standard deviation, 6 divided by the square root of 53. You're going to do this computation, you're going to get a z value of 2.54. So that's your z-score. Now you have to find the p-value. Well, to find the p-value, and again, this is where you can use the calculator. Obviously, you're going to have to use the calculator for this, but they're not requiring the graphing calculator, so that's why I'm showing you how to do this. But what you can do, instead of going to the tables, I never really showed you how to use the tables. You shouldn't need to do that. What you can do now is you're going to go to your second vars distributions and go to your normal CDF. We're going to put in our lower value is going to be, let me draw this for you. Here is the normal distribution. We're going to go to the standardized version with a mean of 0 and a standard deviation of 1. We're at a z-score of 2.54. I'm going to color this little section in yellow over here. I don't know if you can really see that. The p-value is whatever is there. So we need to find that area. So if we go to the calculator, we're going to put in 2.54 for the lower value, E99 for infinity, 0 and 1. Everything's standardized, 0 is the mean and 1 is the standard deviation. If we paste that, we get 0.0055. So the p-value is 0.0055. That's less than 1%, okay? So what happens when we have such a small p-value? We reject the null. So you would say something like, with a z of 2.54 and p let's say p equals 0.0055. That's good. We reject the null. Hypothesis, right? What are we going to say? Now we need context. We could say that, let's say we have evidence that the new ACT prep program increased ACT scores for the seniors at this high school. Okay, so that's how you do this. And this is all without using the tests on the calculator. By the way, if you wanted to just check your work, you can go to stat test. This is just a z-test. We have stats here. Our mu value was 20. Our sigma value was 6. Our x bar was 22.1. And the number of students taking it were 53. We want to see if it increased, so we're there. Let's calculate it. So z was 2.54. That's what we got. A p-value of 0.0054. Just about the same. Should be exactly the same, but okay. So there you go. That's how you would do this. That was just a check to make sure you did this right. So you could always use that check. All right, let's go now and take a look what happens when we want to do a hypothesis test with with proportions, okay? So this is going to be a proportion problem. Here we have John, a starting player for a major college basketball team, made only 40% of his free throws last season. During the summer, he worked on developing a softer shot in hopes of improving his free throw accuracy. In the first 8 games of the season, John made 25 free throws in 40 attempts. You want to investigate whether John's work over the summer resulted in a higher proportion of free throws. Okay, so this proportion, this is going to be, of course, a z test, not a t test. Proportions are always z, right? The thing is, you got some different things to worry about here. One is you still need to know that it's randomly distributed. You'd have to say that, for free throw shooters, a string of attempts would represent a random sampling. You would have to talk about independence. Over the course of the season, he has to be taking more than 400 free throws, which is reasonable to assume. He only played 8 games so far. Now, the normality condition, as you know, for proportions is always n times p has to be greater than 10, and n times 1 minus p has to be greater than or equal to 10. Actually, in this case, it's p hat. We don't have. Actually, no, we do have p. It was 0.4. So n times p is greater than 10, n times 1 minus p is greater than 10. So we could do, he's taken 40 shots, 0.4 times 40. So that you can do on your calculator. You should be able to do that without a calculator, but you can go to your calculator. That's 16. Well, that's greater than 10. And 40 times 1 minus p, 60. That's going to be 24. That's greater than 10. So you've met the normality condition. But how do we actually do, this is the hard part here, because this stuff we've been practicing for a long time. How do we do the actual test? Well, first of all, we want to state our null and alternative hypothesis. Our null hypothesis is that he didn't make any improvement. His proportion is still 0.4. And remember, don't put a p hat here. We're testing the parameter, p. For the alternative hypothesis, we want to say that, no, he improved, okay? Now, how do we do this? Well, just like before, our sample statistic is going to be, look what it says, statistic minus parameter over the standard error. In this particular case, and again, proportions is always z, the statistic is p hat. The parameter is p. And the standard deviation, and again, you might say, I don't know how to do the standard deviation. Well, you should know, but if you forgot, that's where this comes in handy. Here's how you do a standard deviation for a proportion, right? Where are we got? Oh, we got it right here. One population proportion. Standard deviation is the square root of p times 1 minus p over n. And here, if you have p hat, you could use this. So p hat times 1 minus p hat over n. So that's what we're going to be using here. So it's going to be the square root of p hat times 1 minus p hat over n. So let's plug these things in. P hat was, well, let's see. P hat was the actual proportion he got. So P hat I'm going to compute over here. P hat is 25 over 40. 25 over 40 is 0.625. Okay, so we're going to do 0.625 minus P, which is 0.4, over this value. Now here we're going to get, we're going to be doing 0.4 times 0.6 over this whole standard deviation, I'm sorry, over n, which is 40. This z, when you compute this value, is 2.9. Now we need to find what the p-value is based on a z-score of 2.9. Now, when we go to our standardized normal distribution here, 0 is our mean. We are going to find the area in that little section there. We already should know that this is going to be a very small number because in the last problem, z was 2.54. This is even bigger, so the p-value is going to be even smaller, but let's try it. So we're going to go to our distributions, normal CDF. We're going to put in 2.9 to infinity, which is already in for us, and 0, 1, paste. And we get a p-value of 0.0018. P is 0.0018. So you know what happens when you have such a small p-value. You reject the null. Actually say with a p of this, I'm sorry, with a z-score of this and the p-value of this, reject the null. Now give some context. You're going to say, this player seems, we never want to say proves, seems to have increased his percentage free throws with his extra practice, or whatever you want to say in terms of what his treatment was to improve his performance. Okay, but you still need the context down there. All right, so I'm going to put up the next video too, which will be 3 more problems.